Alright class, in this quick video I'm going to talk about certain properties of light such as reflection, refraction, and how to calculate the angles using Snell's Law whenever you have different surfaces for light rays. I have other physics videos on waves for wave properties as well if you look at my physics playlist. First property of light we're going to talk about is called reflection. I think to reflect means to bounce, right? If you look at your reflection on a mirror, it's essentially seeing the light rays that bounce from yourself to the mirror back to your eyes. Reflection is when some or all of a wave bounces back into the first medium, usually that's air, while hitting a boundary of a second medium. That could be the mirror or the glass. When all the wave energy is reflected back, it is total reflection. Again, that's a mirror pretty much where you see the whole image of yourself. If some of it's transmitted and some is reflected, then it's partially reflected. So if you look at yourself under a piece of window pane or glass, you might see a certain part of you, but you won't see the complete reflection of yourself because a lot of the light rays are actually going through the glass. Here's a picture I found about reflection. You take a guess which side is the real side and which side is the reflected side. If you guessed on the right side being the real one, you are right. Now this is a bit tough to see because this is almost complete internal reflection. If you look at the right side, you have your image of your train. The left side, you can see slightly blurred areas there. That's because of the reflection. Not all the rays are actually being reflected. The law of reflection essentially says the angle at which a ray goes in, or called the incident ray, has to be equal to the angle that it bounces off. Think about the reflected ray is the bouncing. You might have played that game Arkanoid where you have that little circle and then it bounces, right? And then you have that little paddle. Brick Breaker's another one like that. The angle which it comes in is supposed to equal the angle it comes out. Now that doesn't always happen. Sometimes when you hit like the side over here, it actually bounces differently, but that would disobey the law of reflection. Anyway, in the law of reflection, you have to have the exact same angles. Now when you're looking at your angles, you need to know what this normal line means. Essentially the normal is a 90-degree angle that's perpendicular to the surface. So the surface was a mirror. You're going to take your 90-degree angle from there, and then the angle of the incident coming in has to equal the angle of the reflected coming out. Now because of that, depending on the surface you have, if it's a very clean flat surface, you'll have reflection that is very easy to see. But if you have weird surfaces or curves, you'll have diffuse refraction. That's light incident on a rough surface reflected in many directions. Now the surface of the ray essentially has to do with the wavelength of light. The longer the wavelength, the smoother the surface. That's because the wavelengths are farther apart between each other. If you look at the picture on the bottom here, let's say I have a weird surface here that's very curvy. The angle of incidence, angle of reflection is going to be the same in each part. However, depending on the curved lines, you might have different angles at which the light rays are bouncing. You might see those funny mirrors in circuses and clowns and whatnot, or it makes you look distorted. That has to do with the rays of light bouncing in different directions. Another main property of light is called refraction. To refract essentially means to bend. So it's a change in direction of a wave as it crosses the boundary between two media. That means two different surfaces like air and glass or air and diamonds, in which the wave travels at different speeds. Because of the different speed, you could see the angle changing. Easy example of this is, let's say you have a pond of water and you see a nice coin over there you want to pick up. You ever notice when you try to reach in to grab that coin, if you start here and then you keep going, it looks like you should actually get it, right? However, when you're actually refracting the light rays are going to bend outward, and that's why you may not actually reach the coin right away. You might have to move your hand a little bit. Again, you have your incident ray, that's the initial ray. You could have your angle of incidence, just like before. Make your normal to the surface, 90-degree angle, it's your angle of incidence. Now the green line here shows what should happen if the surface is the same. Like say there was air to air or glass to glass, it's going to go exactly the same. However, if you have a different surface like glass or different index of refraction, which we'll talk about shortly, the angle will actually change. Here's an example of glass into air. So if you're looking into glass, the angle of incidence is actually smaller than the air, which is a bigger angle, and that's why things will look distorted when you look into glass or if you look into water. Now, in order to figure out what angle a light ray will come in, you're going to use Snell's Law. Now, Snell's Law says N1, or the first index of refraction, that essentially has to do with how well it bends the light. N1 times your sine of your first angle, sine theta 1, is going to equal the N2, or the new surface's index of refraction, times sine of theta 2. So for example, let's say you have air. N1 for air is exactly 1. And let's say it's coming in at a 30-degree angle. You could do sine of 30. So a picture of this would be something like that. Here is your media change. If you do a 90-degree angle from it, this was 30. Now let's say we're bringing that ray into glass. Glass has about 1.33 for their index of refraction. You notice it's bigger than the air was. And let's say you're trying to find the new angle. So now we can use some basic math to solve for that. You can find the left side of the equation. 1 times sine of 30 is just 0.5. I'm just going to write the rest. 1.33 times sine theta 2. To get rid of the 1.33, we could divide on both sides. When you do that, you get 0.37 equals sine theta. In order to find that, you do the inverse sign, the sine -1 button, and your answer is about 21.7 degrees. What that means is that this picture right here, the blue line is going to bend closer to the red line over here. And this will be about 21.7 degrees. So that means the light rays are bending inward. If you went the other way from glass into air, it's going to be the opposite, so it's going to bend outward. Now, because of the Snell's law and changing your angles, you could have different colors of light. Essentially, different colors of light depend on the wavelength of the light. The wavelength has to do with the number of waves that you get, or the distance between it. Now, dispersion in a prism, because light rays are hitting from the air into the glass is going to hit it at different angles, and because of those different angles, you're going to have the different bending of light, and that has to do with all the colors in a rainbow. That's also why you see a rainbow when it's raining out. That's because the water droplets and the mist in the air is actually dispersing light by refraction. Alright class, if there's any questions, please leave a comment down below, and feel free to check the other videos I made in the physics playlist under waves.